From ancient times to the present, in the world of chemistry, some names are destined to be remembered forever for their contributions. At the end of the last century, a gifted chemist, who was supposed to make pioneering contributions in the field of heavy metal independence research, was instead recorded in the annals of history in another way. She was Karen Wetterhahn. An unquestioned experimental procedure, a neglected drop of heavy metal liquid, and in just a few short months, her body underwent a dramatic transformation. Karen Wetterhahn was born on October 3, in Plattsburgh, New York, USA. At the age of Aisharai, she received her bachelor's degree from St. Lawrence University and, in Izotsiwo, her PhD from Columbia University. In Izotsido, she began her career at Dartmouth College in New Hampshire, USA. At the time, she was the first female professor to receive tenure in the chemistry department. Her research on chromium and mercury was also well regarded in the academic world. She was particularly interested in the way these heavy metals are metabolized in human cells and spent years studying how nirvana causes cancer in humans. In Izozor, she founded Dartmouth College's Toxic Metals Superfund research program. This was an interdisciplinary project designed to study common metal contaminants in the environment, with a particular focus on the impact of toxic waste treatment plants on human health. Unfortunately, just in the second year, a shocking laboratory accident interrupted the trajectory of her life. On August 6, she was preparing for some mercury experiments. At the time, most of Wetterhahns' work focused on heavy metals and their toxic effects on the human body. In fact, as early as Izozor Sen, scientists had known that every heavy metal could damage human DNA, but at the time they didn't know how this was caused, nor how DNA was repaired after heavy metal damage. To gain a deeper understanding of how damage occurs through DNA repair mechanisms, they wanted to study the protein core with an NMR probe. However, zinc is not easily detected in NMR spectroscopy, so they used mercury to make compounds. After all, isotopes of mercury can be measured by MR. Her team initially tried to use mercuric chloride standards for this work, but she was not satisfied with the results. In pursuit of perfection and to ensure accurate readings, a most dangerous mercury MMR reference material was finally used: dimethylmercury. What is dimethylmercury? It is a colorless, transparent, and extremely dangerous organomercury compound, known for its toxicity and high volatility, and is considered by the scientific community to be one of the most dangerous mercury compounds. Like other organomercury compounds, it is easily inhaled by the human body and can even be absorbed directly through the skin. Because it is colorless and odorless, the onset of toxicity is often delayed, so those exposed are often poisoned unknowingly. Once in the body, it is converted to methylmercury and binds to proteins and peptides, transporting the heavy metal across the blood-brain barrier. Once in the brain, it interferes with the processes that protect neurons from oxidation and stimulates an immune response, attacking proteins critical to brain function, causing poisoning symptoms to deepen. Because its toxic effects are irreversible, even minor exposure can lead to serious health problems. And it is difficult to remove mercury and its compounds from the body. It is estimated that contact with only 1 ml of dimethylmercury liquid on the skin is fatal. Therefore, even very small amounts of exposure can have serious, even fatal, consequences for the human body. The key point is that dimethylmercury is extremely permeable and can easily penetrate latex gloves and many other materials. This means that even if routine protective measures were taken in the experiment, it might not be possible to completely prevent its penetration into the human body. But these were also things learned later. After discussing the procedure for preparing the standard with the researchers, Wetterhahn decided to do it herself. She put on what she considered safe latex gloves and transferred the dimethylmercury from a sealed glass vial to an MMR tube. At this point, a few drops of dimethylmercury dripped from the pipette she was holding in one hand onto the back of the rubber glove on her other hand. At first, Wetterhahn did pay much attention. She didn't think she was in any danger. So after completing the study, she took off her gloves and left the scene. One day, 3 months after the accident, Wetterhahn began to experience gastrointestinal discomfort and severe abdominal discomfort, and her weight gradually dropped. By the 5th month after the accident, she began to experience mental confusion, slurred speech, and loss of coordination. Eventually, her vision and hearing were also affected. At the end of January, she was tested at the hospital and found to have 19 micrograms of mercury per liter of blood. The standard for mercury in healthy adults is E2 micrograms per liter. Toxicologists believe a dose of more than 2 micrograms per liter is lethal, and these previous phenomena were clearly symptoms of mercury poisoning. Despite Wetterhahn receiving aggressive treatment immediately, her condition continued to deteriorate rapidly. In just 3 weeks, Wetterhahn gradually fell into a vegetative state, completely unable to move, with only her brain and thoughts active, and was very easily agitated. Her husband often saw tears rolling down her face, but in fact, Wetterhahn's brain might not even have been able to perceive the real pain. After a series of ineffective treatments, it was only 6 months from the discovery of symptoms to her death. On June Wetterhahn passed away, less than a year after her exposure to dimethylmercury. In fact, after Wetterhahn learned that her time was short, she told her colleagues who came to visit her 2 things. First, make sure everyone in the lab is tested. Second, she asked her colleagues to do their best to convey this news to the chemical community. Although Wetterhahn had always adhered to strict laboratory precautions, including the use of latex gloves and working outside a fume hood, she still had accidental contact. It turned out that the rate at which dimethylmercury penetrates gloves was much faster than anyone had thought. After Wetterhahn's death, the laboratory had to shorten the sampling interval because the degradation rate of the gloves was so fast. Her colleagues tested the ability of various safety gloves to protect against dimethylmercury and discovered that this tiny nonpolar molecule could diffuse through most gloves in a matter of seconds, much faster than expected. Dimethylmercury could penetrate all brands of latex gloves in less than seconds, and in most cases, less than seconds was enough. The only thing that provided protection was wearing neoprene gloves over laminated plastic gloves. Many chemists were shocked by Wetterhahn's death, because just a few drops of dimethylmercury on protected hands killed a great chemist. They were also surprised by the permeability of dimethylmercury. Wetterhahn's death proved that the standard preventive measures of the time might not be sufficient to deal with highly toxic chemicals like dimethylmercury, and made many chemists realize that they might not fully understand the toxicity of certain chemicals, nor fully understand their nature. For many in the chemistry community, the safety specifications for chemical laboratories are the most precious legacy Wetterhahn left to the world. Later, the Occupational Safety and Health Administration launched an investigation into the accident, eventually finding Dartmouth College DO and requiring the college to hire a new chemical safety officer and revise laboratory safety procedures. It was recommended to avoid using dimethylmercury unless essential. Although at the time dimethylmercury was the most commonly used calibration standard for NMR probes and had certain advantages over any substitute, it was later stipulated that when handling this compound, gloves must be laminated plastic. And for mercury MMR spectroscopy experiments, other materials eventually had to be used. A year after Wetterhahn's death, Dartmouth College, where she worked, established an award in her name, called the Karen Wetterhahn Graduate Fellowship in Chemistry, to encourage other women to pursue careers in science. The school also annually awards teachers for outstanding creative or academic achievement. The school's library and annual undergraduate teaching seminar were also named after her. Her portrait hangs in the Bakerberry Library at Dartmouth College. In any case, even in her relatively short career, Wetterhahn was recognized as a giant in chemistry at the time, a leader in the field of metal independence. What she left behind was not only her outstanding contributions to the field of toxicology, but also an eternal legacy, an awakening to the safety of scientists, students, and the entire scientific community. Her name will always be associated with the rigor of science, the courage to learn, and the truth of life. Although the road of science is full of brilliance, every step must be taken with caution because those unseen dangers may be hidden in every corner of the laboratory. Though her life was short, it illuminated the way forward for countless people, becoming an eternal beacon in the history of science. Alright, this video ends here. What do you think of Wetterhahn's story? You can leave a message in the comment section below. If you think the video is good, don't forget to like, collect, and follow. See you in the next video.